Hi, today we're going to discuss series and parallel circuits, and to do so we're using a water analogy. We use a water analogy because we can see water, and it's very hard to see electrons and how electrons flow through a circuit. Now let's go in the lab and explore how we made this analogy come to life.
Here we are designing resistors that will be used in this demonstration. This laser cutter is cutting out water resistors from a plastic sheet. The resistors have 4 small holes, and they restrict the flow of water. Here we are adding a resistor to the tube that slows down the flow of water. Here we are building our water circuit. We'll use these 2-liter bottles to show how the water level changes as a result of resistors in the tubes.
This is the first circuit we are going to explore. It's pretty simple. We have 2 resistors in series, and we're going to look at how the water level changes across the resistors. Now we're going to simulate this circuit using water instead of electricity. We put a 2-liter bottle at each of the black dots of the circuit to visualize the change in water level. The voltage in this diagram is related to the total water height in the 2-liter bottles of our water circuit. So here's the first resistor placed in the left tube, and here's the second resistor placed in the right tube. And now we're going to fill up this 2-liter bottle on the right. In the water analogy, it represents our voltage source. By filling it up with water, we're putting pressure in the line, and this pressure causes water current to flow through the tube, across the resistor, and into the middle 2-liter bottle. There must be a pressure difference across the resistor in order for current to flow. For current to flow through the left resistor, a pressure difference must build up, so water fills the middle 2-liter bottle. The water level of the middle bottle stabilizes when the flow of water coming into the bottle from the right resistor equals the flow of water leaving the bottle from the left resistor. Now let's mark this water level so that we can later compare it to different resistor arrangements. The flow of electric charge is called electric current because it brings to mind the flow of water, which is also called current, and which we are also very familiar with. The voltage V is a measure of the pressure provided to the electrons so that they can move. In water, if you have 2 containers at the same level and you connect them with a tube, no current flows between them as there's no pressure difference. The voltage is 0. But if you have 2 containers at different levels and connect them with a tube, there's a pressure difference between them, and current flows from higher pressure to lower pressure. The resistor R can be thought of as obstacles to current flow, such as boulders in a river current. 2-liter bottles were positioned at the locations of the 3 black dots. The total current flowing through the circuit is given by I total, which equals the voltage, V, divided by the equivalent resistance. The equivalent resistance, Req, for the series resistors add together. So Req equals R plus R, which equals 2R. I total can be written as V divided by 2R then. We can now solve for V middle, which equals I total times R. Since we just solved for I total, we can plug that into the equation, and we get V middle equals V divided by 2R times R, which equals V over 2. This means that we'd expect the water height at the middle of the circuit to equal half of the total water height of the pressure source on the right. From the experiment, we find a very similar result.